Hey guys, welcome back. Well, guess what? It didn't take a year this time. I've been looking forward to making this video because I wanted to get outside and try using this new ZWO AM5N mount. I heard a lot of good things about it. That's what made me jump in and buy one. From what I heard, it sounded like the guiding performance and periodic error were on par with my EQ6R mount, and I'm perfectly happy with that, especially since I'm going to be probably only using this mount with my two smaller, lighter weight telescopes. Let me show you what I found out. Our agenda today focuses on the AM5N. There are a lot of other videos out there. I encourage you to go watch those. Some of them go into more detail and certainly better produced than this video will be. I just want to give you kind of an overview of the mount from my perspective, some of the features of the mount and its design, and how it differs from the EQ6R that many of us were familiar with before moving bravely into the world of the harmonic drive mount. Also interested in how these screws and bolts are used and how effective they are in performing polar alignment. It's a very similar setup. The azimuth is adjusted by two opposing screws against the center post, and a lead screw is used to raise and lower the altitude of the mount. So nothing new there. The question isn't the newest in the design, it's how well is it implemented. There's no point in buying a mount if you're not interested in the guiding performance. Fortunately, if you use this kind of a mount with a wider angle, that is to say, lighter weight telescope, and therefore probably a wider angle field of view, guiding performance isn't as critical as it is if you're working in the thousands of millimeters for focal length. But certainly within the hundreds that I'll be using it, I'm concerned about it and I want to see it perform well. Fortunately, I did get 4 good nights of imaging and an opportunity to learn how the AM5 works in a real world imaging scenario and learned quite a few things about it. I showed this equipment overview matrix in the last video. We've already covered the things that I wanted to cover in the last video, so I'm not going to go over those. I am going to talk about the AM5N, obviously, and I'm also going to talk about using the QHY PoleMaster with it the way I have it set up. Let's start by taking a look at the AM5 case. Okay, guys, so here it is. This is a ZWO AM5 mount case. It's a hard case with nice foam cutouts inside. And I got to tell you one thing. When you move this around, it is incredibly light. It's almost as if that... Oh. There it is. Okay, guys, so let's stop clowning around. Let's get to work. We're astrophotographers, not astrophysicists. We have work to do. Now, one of the things that I have done is I've put my GT81 on the mount. You can see the pieces of tape here. I've got one piece of tape that's about in the center along the deck axis of the mount, and another piece of tape here on the dovetail bar for the GT81 that marks the approximate location of the center of gravity of the mount. Let's go over and see how I measured that center of gravity location. I'm going to use a simple kitchen scale here. It's rated for 22 pounds, but I'm going to use it to help us get an estimate of where the CG is of the telescope and camera and that whole mess. It's ultimately going to go on the AM5. So let's get an overall total weight of the telescope as it is. So I'm going to turn it on and we'll go into kilograms. And now I'm going to lift up the telescope and place the whole thing on the scale so that it can weigh it as a single unit, get the total weight. Coming up with a total of 7.79 kilograms for the overall weight. And now what I'm going to do is shift it back so that part of the weight is supported on this plastic ruler case, and the other end will be supported on this edge over here, and then we'll get the weight that's supported here, which means we'll know what the weight is over there on the plastic part. And we'll put that about right there. And what we have, the weight that's now supported on the scale is 2.162 kilograms. So we saw in the video the process that I used to measure the center of gravity of the telescope. Let's just go through some of the numbers here so you can get a better idea of what it was that I was actually doing in the video. First thing I did was measure the overall weight. That came up to be 17.2 pounds. What I'm looking for is this distance from the back end of the dovetail plate to where the center of weight, the center of force, acts through so that we can line this up with the deck axis of the mount. We also placed a triangular support under one end, about a half inch from the back end of the dovetail plate, and we let this corner rest on the kitchen scales, and we measured 4.76 pounds there. Now we can just do some simple math where the reaction force R2 times this distance of 13.5 inches to the knife edge support is equal to the total weight of the scope times its distance to the knife edge of the support. And if you solve that equation, you get 3.74 inches, but you add on that 0.5 inches back here. So we're at about 4.24 inches from the back end of the dovetail plate to right here. And this is where you saw that piece of tape that I put on the dovetail to mark, roughly speaking, where the center of mass of the telescope is. And then that's why I lined that up, or the center of rotation of the deck axis. Now let's just say, for the sake of conversation, that you wanted to also do some RA balancing. You don't have to, it's not necessary. Certainly one of the nice features of buying a mount like this and using it with lower weight telescopes is that you don't have to carry around counterweights. But let's just say you wanted to do that or test it out. This is what I'm looking at here. I measured roughly, assuming that the center of mass above the right ascension axis is roughly along the center of the telescope. I know we've got some mass down here, but we also have some mass up here. So roughly speaking, it's about 8 1/8 inches above the center of rotation of the RA axis. Now, if I put on my counterweight bar, at least one bar is 7.25 inches. You could add another bar if necessary. I measured the weight of that bar on the scale and got it to be about 0.76 pounds. Then, if we put on the counterweight at some distance, so the distance below the AM5 mount at the top of the counterweight bar down to the center of that weight, that's the number that we're looking for given the weight that we have to balance this configuration up above on the other side of the RA axis. And if you go through this formula, I won't go through it, but that's what you're looking at in terms of achieving balance. And this is what I get. This is the required weight, so the required counterweight here, based on how far you place that weight from top of the bar. So zero distance is here. That's this zero here. And it would take about 70 some odd pounds of weight concentrated right there to balance the weight of our 72 or our 17-pound telescope. But of course, we're not going to be able to do that anyway. If we come on down, we recognize that once we get up to about 7.25, this is the end of the bar here, that single bar, and you'd have to add on the second bar to get on out to the 14 inches that I'm showing here. Now, one Q6R weight is 11 pounds, so that's 11 pounds, and this tells me where I need to place it in order to balance the GT81, and this says that I'm definitely going to have to add the extra bar if I just want to use one weight, one 11-pound weight, and it would go at about 11 inches from the top. So starting here, going down to 7, and then add on that second bar, and somewhere down here I could use one of those 11-pound weights and place it on the counterweight bar, and it would balance out my GT81. The second choice is I've got two of those 11-pound weights. I could put it 22 pounds, I can move it right here at about 4.3 inches from the top. So, in other words, just use one bar and use both weights. And yes, they do fit for my latitude and the angle that those legs make. I do still have clearance between the counterweights, the EQ6R counterweights, and the legs. So, there's no risk of it bumping into the legs overnight. Okay, so let's move the mount outside and go perform a polar alignment using the PoleMaster. I've got everything put together. You can see there's a little weight bag down here that you can put a weight in if you're nervous about the stability of the mount. I don't think I'm going to be nervous about it with the in GT81. It has a weight bag, which is nice. It also has these spikes here that you can replace the feet on each of the tripod legs with these spikes and tools to install them. So that's nice if you want to use that. Now, this, of course, goes with my EQ6 that I'll be using with the Explore Scientific and my SET. This one I'll be reserving for the GT81 and the Red Cat 51. There have probably been some changes. I'm not familiar with the original version of this mount, but we have a Bluetooth light here. We have the USB port here. We have the ST4 port here, which obviously I'm not going to be using. Hand control port here, power DC in here and a status light. And that's all you've got on the front. On the side, my understanding is there used to be something here that they had, but it created some cable management issues, so they got rid of it in this version. We have a saddle. The saddle is actually very good. I'm a little concerned about these very small knobs and being able to get enough torque to lock your scope down conveniently. But other than that, the saddle is very nice. It has a Vixen and a D-style interface, which is good. All my plates are D-style. And even though I don't have a use for them yet, there are these two M6 threaded holes here. May have a use for these ZWO ecosystem and the ASI air and whatnot. I don't know, but I always like having threaded holes. It's always something you can do with them, right? And then on the other side of the saddle, it looks like a couple of M4 holes there. That's the on-off button. And then down here, I've got a little cable management thing that we'll be looking at later once I get the scope back onto the mount. Now, on the back, I've got my latitude programmed in at about 33 degrees. We'll be making adjustments for that when we do a polar alignment. You'll unlock this and this. That locks the altitude position in. And when we unlock it, we can turn this thing here and make adjustments. We'll see how well that works when we do polar alignment tonight. Azimuth control, azimuth adjustment knobs here and here. Very much like the azimuth adjustment knobs on the EQ6R. And another kind of a bonus, I think, there is a plug down here, threaded plug, for the counterweight bar if you should need a counterweight bar. The EQ6R, of course, has a counterweight bar, but it also has a separate counterweight bar, so you can make it a dual length thing when you need to carry a large payload. But it turns out that this interface here with this counterweight bar from the EQ6 is entirely compatible with the AM5N, so I can just plug that in if I need a counterweight. Another cool feature, something I really like with the saddle, is this interface down here. You can see we have DC power coming in here and a USB-C port here for the data. This is great because that'll come down from my Ultimate Power Box and just plug into these two ports, and there won't be any problem with cable snags, whereas with my EQ6R, the data port and the power come down to what amounts to the this portion of the mount, the RA portion, not the deck portion. In other words, the equivalent of here on the EQ6R. And I have to have these two cables going up to the power box, and therefore I have to leave a service loop so that you can make all of the deck movements that you need to make without getting a cable snag. So it's nice to at least avoid the potential of a cable snag with the mount there. Now I'm ready to start doing some polar alignment and maybe even some imaging tonight with M33 rising. I've got to get approximately set up near polar alignment so that when I use the Polemaster, I can zero in on Polaris. Now, what you'll see here are the legs about 3 inches from the edge of the slab. According to the surveyed plat I have for my house, this slab edge here is 37 degrees and 41 minutes or 43 minutes off of true north. That over there is about true north. And so what I need to do with the legs set up as they are here, that takes out 30 of those degrees. And so now I'm just left with 7 degrees and 43 minutes to compensate for. Well, if you take 7 degrees and 43 minutes, which is about 7.71 degrees, take the sine of that angle and multiply it times the distance between the legs, which is 32 inches. That gives you about 4.3 inches. So what that means is I need to rotate or pull that leg, the one closest to me, move it out another 4.3 inches, rotating about the front leg. And then that will give me a darn near good polar alignment, certainly good enough to make minor adjustments using the Polemaster and the software for that. Okay, so I've made the changes. Let's take a look. This should be about 7.3 inches away from the slab edge, and that's about right. So that's what we're looking for. We are now looking at more or less due north. I hope to take images all night tonight. Now, one of the first things, obviously, we're going to do here is do the polar alignment. For polar alignment, I'm still using my Polemaster, but let me show you what I have and what I'm going to be using going forward with all of my telescopes, because it works for all of my telescopes. So here you can see this Los Mandy interface here. I bought this a number of years ago, the black element there with the tightening screw. This I bought for my DSLR, never used it. This silver part here is something I had made. I was doing some work and having a machine shop make some parts for me for work, but it was shortly after I bought the Polemaster, so I had them make this aluminum part here that had the same bore opening as on the EQ6R. So I just moved my adapter off of the EQ6R, that's it with the thumb screw up there, and locked it into place inside the hole here. There you go. And then I can just connect up the Polemaster to the adapter as if it were on my CGM or on my EQ6R, and there's no problem with that. All I have to do now is just slide this up under the dovetail bar, and every one of my telescopes has the same dovetail bar, so that won't be an issue. And let me get that put on, and I'll show you what that looks like. Okay, so here's the Polemaster attached onto the end of the dovetail bar. It's going to work great. I'm not going to have any problems at all with this and using it with all my telescopes. It saves me from buying another adapter for this mount. I can just use this arrangement on all of my scopes and I'll be good. Now, when I come out tonight, I'll just plug that cable into my laptop that I'll bring out here and run the Polemaster software from it. Meanwhile, the mount will have to be on because I'll be using the hand control on the front end of the front end of the mount to move the scope as I make the adjustments required by the procedure that we have when we follow Polemaster. There, we're connected up to the Polemaster. The brightness looks fine. We'll cancel that out and we'll double click on Polaris. And then we'll have to rotate those sliders around until the pattern of circles matches the pattern of stars. Those of you who have a Polemaster know this all too well. That's pretty good there. And we'll say OK. We don't need to accept a previous alignment or whatever that is. I always say just cancel that. And now we have to pick another star other than Polaris and follow it around as we rotate the scope. And this is where I'm using the hand controller to make the adjustments as indicated on the screen there. I just need to rotate this about 30 degrees and it's going backwards. It's going backwards because I'm sitting behind the scope and the hand controller is designed to be used from in front of the scope. So when I press the right button, I'm getting left motion and that's what's happening here. It doesn't really matter because it just needs to get a couple of points on the circle here, so I'll reselect that same star and rotate it again. I guess I'll keep going the same direction I was going, and you'll see that we're going another 30-ish degrees. Now keep in mind what we're doing here, because I'm going to show you the current draw for this period of time. We've done that now twice. We've rotated twice, and now we're going to double click on the star. There's the line that the star presumably followed, and we're going to say that's correct. Now watch a weird thing that happens here. As you press correct, the star kind of gets out of alignment with this circle, but then gets back on eventually. I don't know why that exactly is. See, it drifts off. I don't know why that is. That seems like it may be a deck issue. Not sure. It doesn't affect the results, as we'll see, but it is a curiosity. And then it comes back to the home position after pressing the home button on the hand controller. Now we're done with the hand controller, so we just say that's correct. It more or less followed the path. Now we have to select Polaris again, and now it's going to show us where the center of rotation is of our mount, which is that green X. And we need to get that lined up with the red circle there. And so we need to put Polaris in that spinning circle. And if you hover your mouse over that, it'll give you that zoomed in image in the upper left. And now I'm going to be modifying the azimuth and altitude knobs behind the AM5. And initially I'll start with the altitude. So I'm unlocking the screws and then I'll change or play with that lead screw to move it in the correct direction down to about where it's supposed to be. And now I will go ahead and move the azimuth settings by loosening off one of the bolts and then tightening the other one and move it until I see it in that magnified portion and then make a final couple of adjustments to bring it up to that X. Now, you don't have to be too precise here. You could just get it in that circle and you're close enough. I find though that I just go ahead and make it as accurate here as I can, then I don't have to make an adjustment in the next step typically. So it looks pretty good right there. We're going to say OK. Now it's going to ask me to rotate or to select Polaris and then find the template again and line it up with the stars. Looks pretty good. And we'll do the start monitor, and now the green and the red boxes need to be lined up. And because I went the extra effort to line it up in that previous view, this is perfectly lined up. So there's nothing to do here. I wouldn't want to make any changes at this point with what I'm seeing here. This is perfectly fine. And as I tighten down the bolts, nothing really moves at all. So everything looks good. And we're done. Here's the final pole master screen, and you can see that we have our pole aligned as precisely as it can be aligned visually anyway, with the center of rotation of the telescope, the center of rotation of the mount. So everything looks perfectly good here. Very easy to make the adjustments. And as you can see in this screenshot of the final screen of the pole master driver software, you can see that the axis of rotation of the scope, the red icon, is perfectly centered on the pole icon. So this should represent a very good polar alignment. First night I did imaging, I performed a guiding assistant test where essentially the mount is allowed to drift unguided, and it allows you to compute the RA drift arc seconds per minute, if you will. And then that in turn, based on where you're pointing in the sky, that in turn tells you what your polar error is. And after 80 minutes, PhD2 tells me that I had only zero point 0.3 arc minutes of error. So that's about 20 arc seconds. That is not bad at all. Certainly far better than is necessary with this scope and this setup. But it goes to show you just how easy it is to make the adjustments with the mount to achieve an accurate polar alignment. So what I've got plotted here is the current draw as output by the Pegasus Astro Ultimate Power Box during the period when I was doing that fast motion for the polar alignment. You can see the first rotation here at 30 degrees, and the second rotation, another 30 degrees, roughly speaking, and then a return to home. And what we should be seeing is that as we move away from the home position, we started at the home position, moved 30 degrees. At this point, during this motion, as the scope is rotated over, gravity is helping us to pull the scope over. So it shouldn't require more amps to move the mount and the scope during this phase because we're not fighting gravity. Gravity is actually helping us. It also helps us here, and we should need less amps to move 30 degrees. But when we move back the other way, when we're moving from a position 60, 70, 80 degrees over and we're moving back to the home position, now is the time when the motor is having to fight the gravity torque. And who knows, it may be that we're seeing some slight indication that as we start where gravity torque is having a higher effect, the current draw decreases as we get the scope closer to the home position. This may be an indication that the motor is in fact working harder and drawing more current as it moves the scope back to the home position. Now, this can affect you during tracking. For example, when the scope is on the east side of the pier and moving up, the motor is going to have to work harder on the east side of the pier than it will when the scope is on the west side of the pier. Also, perhaps there might be some effect during guiding when it's trying to issue commands in one direction versus the other direction because it's going to have to fight gravity torque in one direction, but not the other direction. So it might be kind of an interesting experiment to put on those two counterweights I have from my EQ6R and just see if that affects the guiding and see if it affects even this particular graph while I'm doing a polar alignment. ZWO gives you this sheet of paper with your AM5N. It seems to be related to your serial number, so it seems to be quite specific. And it shows the periodic error and the worst case periodic error. Now, one of the things that's kind of interesting about this upper graph here, they seem to have run the motor a full 360 degrees. I'm not sure why they do that. After all, when we use the telescope, we're only going to go plus and minus 90 degrees relative to home position. I wonder if they performed this test to find out where the best performance is in terms of periodic error and then plot the gears within the mount so that we're only using the best part of this periodic error? I suspect I know the answer to that question, but it would be nice to know if you had a mount where you could have access to only this portion of the periodic error and not have to deal with the 180 degrees the other side where you have this kind of periodic error. But nevertheless, that's what they're showing us. And then they zoom in on the period region of the graph where periodic error is highest, which for them is down in, for this particular amount, seems to be up in this area here. So let's take a closer look at this periodic error and see what they have. The fundamental period of this, if you want to call it the high frequency portion of the periodic error, is about separated by this a distance here between these peaks. Now, I say the high frequency part. Notice that going back to this graph here, you can see there is a very low frequency. It's just varies over the course of what amounts to 24 hours here. It varies just like one period over 24 hours as you go fully around the circle. So that's a very slow drift. PhD2 can keep track and compensate for that without any trouble. Where PhD2 could possibly have an issue is dealing with this faster or this higher frequency period and the faster rates that's going to have to make an adjustment. Now, if we take this little arrow here and slide it over to their grids, we'll see that it's almost exactly the two between two grid lines, and we have 1.2 degrees, which if you bring in the sidereal rate, you get a 280-second period. And I have seen that number quoted before with the AM5. What you're seeing here is a 280-second period, but for comparison, my EQ6R I think is something like 480 second. So it's a quite a different period here. That also means that we've got to make adjustments, compensate for this error rate over a period of 144 seconds. In other words, half that period, we've got to compensate for this drift. And again, I think this is a small enough number that PhD2 can handle that. We'll take a closer look at that. Now, I did do a guiding assistant run for about 80 minutes, as I mentioned before, and this is where you just let the mount go, let it drift, and calculate the slope here. And if you let it run for a good long time, it'll give you a very accurate assessment of the polar alignment error. And that's what we looked at before. Is that number comes from, it's calculated by the PhD2, but it comes from the slope of this line here. These squiggles, that's the periodic error that we're seeing. It's just superimposed on this drift rate because of the polar alignment error. And if we take that blue portion, the RA portion, take out that trend line, that linear trend, this is what we have. This is sort of comparable to the ZWO graph that they were giving us. And if I do an analysis of this, I can find out, yes, in fact, I'm getting the 288-second period, and my number here from peak down to trough is about 11 arc seconds, which is what they're reporting. So that's 11 arc seconds in roughly 144 seconds, half the period that PhD2 has to keep up with. And so that turns out to be about 0.076 arc seconds per second that PhD2 needs to compensate for during guiding. Otherwise, it'll get away from you. But again, this is a pretty small number, certainly on comparable to the kind of number I have with my EQ6R and getting perfectly good guiding with that. So I don't think this is a problem at all. Another thing that I'm seeing here is that my numbers that I'm calculating with PhD2 guiding assistant data are exactly what ZWO is reporting in that spec sheet they give you from testing the mount back in their facilities. So everything is checking out there. The mount seems to be doing what it's supposed to be doing, and with a periodic error that is, like I say, it's on par with what I have for my EQ6R. It's just a little bit faster period than what I have with the EQ6R, but I don't think that's a showstopper by any means. Now, let's take a look at the guiding performance. If I take all of the guiding data that I had for those 27 hours of just pure guiding, this is what I get. You're seeing a curve for the deck, you're seeing a curve for the RA axis, and then you're seeing a combined or total RMS. This is what you're seeing when you look into PhD2 and you say you look at the total RMS, but you're seeing an instantaneous readout more or less of the total RMS. And by looking at a curve like this, what I can do is say something like, well, 80% of the time, that's the 0.8, 80% of the time, my total RMS is less than 0.82 arc seconds RMS. Okay, so that is pretty good. I wanted it to be better. It's perfectly fine for the scopes that I'll be using on the mount. But we also should remember that this is a statistical phenomenon. And one of the things that I caught, again, climbing that learning curve, darn it, I forgot to press the button in PhD2 to do multi-star guiding. So almost all the data I have was captured while guiding with a single star. Multi-star guiding helps you to eliminate or average out the effects of seeing, and so you get a cleaner, more accurate adjustment for mechanical effects as opposed to seeing effects. So I went to that last night. I only had about 3.75 hours to collect data before clouds moved in, but during that 3.75 hours, this is what I got. It's a much better looking curve where now if we go and say, well, 80% of the time of guiding during that night, I was down at about 0.55 arc seconds RMS. Now that number is almost exactly what I get with my Skywatcher. I get about 0.56 RMS, arc seconds RMS with the Skywatcher, and it doesn't matter whether it's the lightest weight telescope I have, the RedCat 51, or this scope, or the Explore Scientific 700 millimeter scope, or the SCT. The weight doesn't seem to play a big role in this. The RMS value we're seeing is dominated mostly probably by seeing effects, but the rest of it is a small amount of contribution from the mechanicals. And the mechanicals for this mount, the AM5N, appear to be on par with the EQ6R mechanicals, and that's good news. This is what was advertised. We are getting it. At least we did this night. More data is necessary. I'll have to make a summary of this after using this mount over many nights, collecting data, performing the analysis. But I couldn't be happier with this result because hey, this is one of the reasons why I bought the mount. Okay, now what about the win some, learn some summary? Let's start off with the learn some. There are no showstoppers here. No uh, no super bad news about this mount. A few things that I learned along the way, though, and bumped into, and just need to adjust the way I work with this mount versus what I was doing with the EQ6R. First thing I learned is, wow, you better start the ASI mount server before pressing the connect button in Nina. It does not like it if you press the connect button in Nina because it doesn't start the server. It doesn't see the server and it can't start it. This is different from by using the EQ6R and Green Swamp Server. When I connect them out in Nina, it starts Green Swamp Server, and that's pretty handy. This is not a big imposition. It's just you got to change the way you do it. You've got to start the ASI mount server before connecting in Nina. Another thing that caught me off guard is that the AM5 stops tracking at the meridian. It doesn't track past the meridian. I don't know of any setting that would let you do it. There are some settings within Green Swamp Server to allow you to let the EQ6R go past the meridian, and then when it gets past and finishes up the image, it'll look at the Nina settings and flip the scope. And you never really lose time or much time during a meridian flip. Here, things are a little bit different. Here, I need to set the pause before meridian. I had to set it 0 for my EQ6R. Set the pause for something like 2 minutes. So at 2 minutes before the meridian, the AM5 is going to turn off tracking and just sit there. The next thing is the meridian flip is going to occur when the sum of these two numbers, the maximum minutes after the meridian, is when the flip will occur. So that for these settings that I have shown here as an example, you got 3 minutes after the meridian and 2 minutes before. So once you stop, the 5 minutes later is when the meridian flip will occur. There's no periodic error correction option that I'm aware of in the driver. You have that option with Green Swamp Server. I do program periodic error into my EQ6R. Honestly, you don't need it. I suspect PhD2 can compensate for any of the periodic error that we're seeing either in the EQ6R or the AM5, so it's not really a problem. I just like to do it. There's no definable park position in the ZWO drivers. The home position that ZWO has defined in their driver is counterweights down and scope pointed north or south, depending on where you are. And that's what I want. That's what I usually consider to be park. That's not what ASCOM considers to be park. Now, another thing that I find hard to get used to is not having the deck or RA clutch releases. I like to, for the EQ6R, release the clutches so I can quickly swing the scope around to all possible orientations and confirm that I'm not going to get any cable snags. I also like not having to power up the mount in order to do a polar alignment. I just undo the clutch, rotate the scope over, set the clutch, do the work on the screen for pole master, rotate it again, and then rotate back home. Never having had to power up the scope. Now I've got to power up everything. Now, on the winsome, I think this category wins out for me. First and foremost, there's no reason to buy a mount if you're not interested in the guiding performance and the periodic error, good periodic error. And these performance metrics, most important performance metrics, are as advertised by ZWO. I'm getting performance that is, frankly, quite on par, if not darn equivalent to what I'm getting with my EQ6R. So the second winsome is lightweight. I can't tell you what a difference it is to just be able to pick up the mount and the scope and walk out of the door or come back in with the scope. The attitude and azimuth adjustments that you need to make small adjustments to while doing a polar alignment are very well designed. I found that when I was locking things down either in altitude or in azimuth, there wasn't a corresponding jump in the star position. It was very consistent. It just held its position. Finally, there is this nice feature of the built-in home position. You can just, if you have the hand controller, you just press that button for 3 seconds and it will go find the home position. And the home position is what I normally think of as the park position. Now, that does change how I have to program the sessions in Nina. For example, my shutdown procedure at the end of a night, I'll stop guiding, and then now there's a new button called Shutdown PH2. I'll implement that. But the things that affect the mount, now I don't tell it to go to park position. I tell it to find home, and then I set tracking to stop. And I love the saddle design on this mount. The power cable and data cable feed throughs on the back of the saddle just eliminate 2 more cables that could get caught on something. So on a balance here, the win sums definitely win over the learn sums. I'm very happy with it. Easy to use. I've been learning about it these past 4 nights of imaging, and I'm looking forward to getting back out there and doing some more imaging with it and learning a little more about this mount. But yeah, so far, so good. Okay, guys. Well, that's another video down. I'll see you next time. Clear skies. And if I don't talk to you again, happy holidays from Texas. See ya.